Okay, so on this one you got a toboggan racing down the hill. Okay, so there's your hill. Okay, that's a toboggan, right? And it's racing down the hill. I'm not going to try and draw a person on it. Okay, my people have their legs and their arms come right out of their heads like a 2-year-old draws them. Okay, so at one point it's 30 meters above the bottom, moving at 14 meters per second. Shortly thereafter, the sled is moving at 23 meters per second. How far above the bottom is it at this point? All right, so get a drawing of it if you want, or just write your givens, whichever makes more sense to you. Okay, I'm going to give you a few minutes to see what we remember from yesterday. This is one of the ones that's like the second most involved algebraically. I forgot to give you something in that question. Not that it matters. Let's see. Okay, so we got this toboggan. It's going down the hill. We know that at its initial point, it is 30 meters above the ground and moving at 14 meters per second. Okay, a little while later, they don't specify the bottom, which is important. Okay, they tell us that it is moving at 23 meters per second. We are looking for how far above the bottom it is, or the final height in this case. All right, so is there any mention of any forces here? No. Okay, so is this a conservation of energy question? Yes. Okay, plus they gave us 2 speeds and 1 height. They wouldn't give us that in a work energy theorem problem. All right, so work equals, whoop, I got work energy theorem in my head. EI equals EF. Okay, the mechanical energy is not changing here. How do we calculate mechanical energy?
EPI, so that's EK.
Right, our potential energy, in this case the initial values, okay, plus our kinetic energy equals our final potential energy plus our final kinetic energy. Remember, all we're doing is saying still that the mechanical energy initial and the mechanical energy final are equal. All right, what I'm looking for is HF, which is part of this. Okay, I want to get that by itself before I go putting all the formulas in. So what do I have to do to get EP final by itself?
Subtract EKF.
Right, subtract EK final over to the other side. All right, so I've got EP initial plus EK initial minus EK final equals EP initial. Now I can put in all my formulas. Okay, so that'll be M times G times H initial plus 1/2 MV initial squared minus 1/2 MV final squared equals M times G times H final. So all I've done is put in the formula for each one of those terms. Okay? Now, since I forgot to put mass on there initially, was mass important?
No.
No. Okay, I can put 50 kilograms in 4 times if I want, but I don't want. Okay, so I'm going to take mass out of there because I'm solving for a height or a speed. I can do that. If I'm solving for energy, then I have to leave it in. Now that I've done that, okay, I need to get HF by itself. What do I do with the G? All right, divide both sides by G. All right, I've got my manipulation done. Now I just need to plug in my numbers. So H final is going to equal 9.81 times 30. So my initial value is there, plus 1/2 times 14 squared, initial value there, minus 1/2 times 23 squared, that's a final value, and then divide that by G, 9.81. All right, so we're punching that all in. I forgot to start my calculator. Now I'll have to wait for the hamster to wake up. Okay, so 9.81 times 30 plus 0.5 times 14 squared minus 0.5 times 23 squared. Okay, and then divided by 9.81. Okay, so they're quite a bit further down. Okay, they're now at a height of 13.03 meters. Okay, how did we do with that one? Yeah, still pretty patterned though, right? Like the first half of that is the same no matter what question you're doing. Okay. All right. Okay, there you go. That's a good one. All right, so we got the car driving off the cliff. Okay, which is like an old movie trope, right? Cars always drive off cliffs. And what do they always do when they hit the ground?
Explode.
Right, do you know how rare it is for a car to actually explode? No matter how heavily damaged it is.
Pretty
okay?
rare.
Yeah, it's pretty rare. They're all designed to not do that for some reason. Okay, you know, like safety or something like that. Okay, but yeah, they are all designed to not explode. Really, it's quite rare. There has to be really some sort of problem with fuel vapor, okay, for an ignition event to happen. So it's pretty rare. But they're going to do this. They're going to follow a projectile arc that encounters the ground eventually. Okay, we do know that we are looking for the height of the cliff, which is the initial point in the question. We know that at that point they are cruising off the cliff, like Thelma and Louise, okay, at 25 meters per second. Best part of the movie, by the way, is when they drive off the cliff. Okay, I can't stand Susan Sarandon's voice. It's like nails on the chalkboard. It is 53 meters per second. Incidentally, I was the only person who cheered because the movie was over then. All right, EF equals 53 meters per second, and that happens at a height of 0. Okay, so that's important. Any work being done in this question? Nope. All right, so we got EI equals EF. Okay, so that's going to be EK initial, we have that, plus EP initial, we have that. It's part of what we're looking for. Okay, EK final, we've got that. Oh, not equals, plus. EP final, do we have any of that? No. No, that's 0. Okay, our final height is 0. So that simplifies things a little. Okay, I'm looking for EP initial. What do I have to do with EK initials? Right, move it over to the other side. So I'm going to have initial potential equals the final kinetic minus the initial kinetic. Then I can put in my formulas. M times G times H initial equals 1/2 mv final squared minus 1/2 mv initial squared. Okay, we can cancel off all the m's, which is good. I once again forgot to tell you the mass of the car. I do that a lot on practice questions because I always know it doesn't matter. And then what do I have to do with G? I have to divide it over to the other side. All right, now I can put my numbers in. So height initial will be 1/2 times 53 squared minus 1/2 times 25 squared divided by 9.81. Let's find out how high this cliff is. 0.5 times 53 squared minus 0.5 times 25 squared. Okay, and then divide that by 9.81. Well, you'll probably have to take a breath and scream twice. Okay, that's a pretty tall cliff. You're going to be falling for quite a while, okay, on that cliff of 111.31 meters. Okay, everybody all right with that one? Mm-hmm. Okay, we haven't solved for one with speed yet today. We did yesterday. We haven't solved for one for speed. So, yeah, there we go. Okay, so skydiver jumps out of a perfectly good airplane, okay, moving at 90 meters per second. Now, the plane's not diving. The plane's moving horizontally. Does that matter? No. Energy is scalar. Okay, you have energy because you are moving. When you jump out of a plane, you're moving the same speed as the plane, at least for the first instant until air starts to slow you down. Okay, but you are moving along with the plane. Okay, so important to know that for the context of this question. All right, so we jump out of this plane moving at an initial speed of 90 meters per second. And again, which direction you're going makes no difference. Okay, I mean, you're eventually going to be moving mostly vertically, but you're actually always going to be moving horizontally at 90 meters per second. That's just part of how projectiles work, how falling objects work. Okay, all right, and you are at an initial height of 10 10,000 meters. Okay, how fast will the diver be falling? So we're looking for VF, okay, when they are 8,000 meters off the ground. All right, so there's our givens. Okay, any work being done? No, that's the reason why they said he didn't open his parachute. Once you open your parachute, you don't fall as fast. In fact, you don't accelerate. You fall at a constant velocity when your parachute is open. Okay, so EI equals EF, right? And we have initial potential. We also have initial kinetic. And we have final kinetic because we're being asked about it. And we have final potential because we know how high above the ground we are. All right, so we know all of those values. None of them are 0. And what I'm looking for is part of this. What do I have to do with EPF? Subtract it over to the other side. All right, so initial potential plus initial kinetic minus final kinetic, or sorry, minus final potential, sorry. Final potential equals final kinetic. Okay, plug in our formulas. Once again, I didn't tell you the mass of the skydiver. Okay, plus 1/2 mvi squared minus mghf equals 1/2 mvf squared. All right, we don't know the mass of the skydiver because Coderre keeps forgetting to put it on there. All right, I want to get VF by itself. What do we do?
Subtract EPF.
Oh, I already did that.
Oh.
Divide by 1/2. Yeah, I got to move the 1/2 over to the other side. All right, that gives me VF squared. What do I want? I need the square root of that. Okay, so plugging in all the numbers here. 9.81 times 10,000 plus 1/2 times 90 squared minus 9.81 times 8,000 divided by 1/2, all square rooted, will give me the final speed of the skydiver. 9.81 times 10,000 plus 0.5 times 90 squared minus 9.81 times 8,000 divided by 1/2 square rooted. Okay, so they are moving at 217.58 meters per second. Fast?
Yeah.
Yeah. In the real world, could you ever fall that fast? No. You would hit terminal velocity well before you get to that speed. Okay? And terminal velocity is just caused by, as you fall through the air and increase in speed, the force of the air pushing back up on you, air resistance, eventually balances and becomes equal to the force of gravity and you stop accelerating. Now, make no mistake, terminal velocity is still really fast. Okay, and you don't want to hit the ground going that speed, okay, but it's not 217 meters per second either. Okay? Air resistance really starts to slow you down, and that's why we use parachutes. You open your parachute, you increase that resistive force, okay, and your terminal velocity is a lot less when the parachute is open. It's also why those guys that do all the, like routines in the sky, they move, they change their shape, they put their hands out to fall slower, they tuck in to fall faster. Okay, that's how all of that works. 217 meters per second would be 783 kilometers per hour. Fast. Yeah. Yeah. Pretty fast. Okay. Now, it's not speed of sound fast. Speed of sound at 0 degrees Celsius is 332 meters per second. Okay. So they're not into the sound barrier or anything yet. Okay. But they're certainly going pretty fast. Okay. How are we feeling about these?
Good.
Okay. So it's the algebra, right? It's getting everything moved around that can be a bit confusing. Okay, but rest assured, guys, remember, the first part of this is always the same thing, right? We establish that no work is being done. We can say everything is equal, okay? We determine what we're looking for and isolate that, Then we put in the formulas, manipulate and isolate, plug in our numbers and solve. Okay, it's really, really patterned. The trick is just figuring out what do you have and what are you looking for. Okay. All right, I'm gonna give you about a 5-minute break here and then we're gonna look at a couple others. So guys, with 15 here, okay, sometimes it can be a little bit confusing, but here's what number 15 is testing. Does the mechanical energy ever change as that rock falls? No. No. How much of it is potential and how much of it is kinetic? Does. Can you calculate the mechanical energy at any point using the first value? Yes, because at 20 meters, it's all what?
Potential.
Right, because it's being dropped. So if you go if you go 2 times 9.81 times 20, do you have the mechanical energy of the rock all the way to the bottom? Okay, that means to calculate the kinetic energy only requires you to go that number minus however much potential you have at all of the heights given. Agreed? So it's not about you having to do an EI equals EF calculation at all. It's just that understanding of this number that I calculated using the first values never changes, this 392 joules. Okay? It's always that number all the way down for mechanical energy. All you have to do is make sure EP and EK add up to 392 joules. Okay? Does that sort of make sense? It's just reviewing that concept of mechanical energy doesn't change and it's EP plus EK. Okay, couple of things here, guys. So obviously on the quiz, I see a few of you are already working on that, which is great. Those questions are a bit more context-based, right? Like you have to read a story. And there's a few things in there that, you don't get the givens unless you have like a full understanding of the picture of what's going on, which is exactly what I intend, okay? That is the kind of thing that you're going to see going forward in this course and in Physics 20 and Physics 30, okay? So it's just kind of preparing you a bit for that. So have a look at that, and if you have questions, pop in and see me, okay? Tomorrow's your quiz on work energy theorem, okay? So have a look at that. Was the first question on the quiz a conservation of energy question?
No.
No, it was a? Why did I do that? To see if you can tell them apart. Okay, I threw one on there on purpose just to see if, hey, oh, this one gave me force. It's not a conservation of energy question. Okay, because on a unit exam, are you going to get both?
No.
Yeah, you got to be able to tell them apart. Okay, so that's kind of what I was doing there. So tomorrow quiz, Monday, unit exam review, Tuesday, okay, efficiency and covering anything we need to polish up before we go to our exam on Wednesday. Thursday, go over the exam and start unit 4, Friday unit 4. Then we come back after Christmas, okay, we finish up unit 4. Your unit 4 exam will be January 15th. I just looked at how many lessons I have to teach and how many days are left. That's where it falls. Okay? That is the second last day of classes. We may be done a day before that, but that's when the exam will be. Okay? All right, good job today, guys.